Humanity has been bestowed with great gifts. Perhaps greatest of all is our imagination. Because ultimately, it's our imaginations that enable us to shape the world around us. The most obvious examples of that are the great buildings and architecture all around us. But which works of architecture should we see during our lifetime? Find out in Top 10, The Art of Architecture. In this installment, we visit the top 10 designed and engineered bridges of the world, beginning with the oldest and ending with the aesthetic shock of the new. Bridges not only make our lives easier, they can also make the world a more beautiful place. They are a living metaphor for making connections whether you walk or drive over them or pass under them in a boat. So now on Top 10, let's cross over some of the greats in bridge design. Brooklyn Bridge, New York City, USA. The Big Apple in all its glory. You think of the Statue of Liberty, the Empire State and Chrysler buildings, and the Brooklyn Bridge. It connects the boroughs of Manhattan and Brooklyn by spanning the East River. The story of the Brooklyn Bridge has it all: a family dynasty, the American dream, and the very 19th century type of faith in technology as the solution to all our problems. The man you might call the father of the Brooklyn Bridge was an American architect and engineer of German descent, one John Augustus Roebling. Roebling began work on the project in 1867. After his untimely death, Roebling's son Washington Roebling took over construction. Washington decided to use caissons, large watertight wooden vessels which scrape along the riverbed to build the massive foundation of the Brooklyn Bridge.
I think from everywhere, every aspect, all the details even of that bridge, I mean, it feels very European to me, which is the basis of New York. In its beginnings were European, and so it feels like beautiful European bridge architecture to me, but it sits perfectly in New York and in this place.
Construction commenced on January the 3rd, 1870 on the Brooklyn banks of the East River. A caisson sized 50 by 40 meters was lowered into water. After the caisson's steel blades dug deep into the riverbed, the hugely ambitious construction began. There were two groups of workers, one which worked above the waterline on top of the caisson, building the foundation of the bridge tower out of huge granite blocks. The second group worked inside the caisson, digging down until they reached solid bedrock.
You feel that it's a really strong bridge, and you feel like it's going to support you, and you feel in this architecture, this heavy brick and stone architecture, you feel early New York. You know, you just feel that it's in the right context.
Working with the air compression chamber was difficult and dangerous. 27 people lost their lives to make the Brooklyn Bridge a reality. Many of the workers suffered from decompression sickness, including Washington Roebling himself. When the second Manhattan side tower was built, with its foundation laid at much lower depths, Washington fell ill. When he did so, he turned to his wife for support. he explained all the mathematics and mechanics of the bridge's construction to Emily so that she could take over in the event of his death. In the end, it was Emily Roebling who saw the project to completion.
It remains the oldest suspension bridge in the USA and continues to be a historical landmark. It's an integral part of the New York skyline.
When both bridge towers were finished, they stood over 80 meters above water level, instantly becoming the tallest structures in the Western Hemisphere at that time. For its day and age, before electricity, the motor car and skyscrapers, this was astonishing. Brooklyn Bridge was inaugurated on May the 24th, 1883. 1,800 meters long, and with a span of nearly 500 meters, it was until that time the largest suspension bridge ever built. It cost $15.5 million, an enormous amount of money at the time. Over the decades, this national landmark has been reconfigured to include a 6-lane road and a path for pedestrians and cyclists, but lost nothing of its charm. Dom Luís I Bridge, Porto, Portugal. In the Portuguese city of Porto, known for its sweet dessert wines of the same name, you will find one of the most beautiful bridges in the world. The Dom Luís Bridge is located in the historic centre, high above the valley over the river Douro. The magnificent bridge was built in honour of Ludwig I, the Habsburg King of Portugal between 1881 to 1886. The architect was the German designer and engineer Theophile Seyrig, a disciple and colleague of Gustav Eiffel. Yes, that's as in the Eiffel Tower.
This bridge hit a record for the biggest trussed arch bridge at the time it opened. It's an elegant structure, and its filigree-like construction gives it a special lightness.
The so-called truss arch construction of the Dom Luís I Bridge uses thousands of triangular or rectangular bars which give it its strength to withstand the elements. This double-deck bridge, intended for horses and carts, but carrying trams and automobiles to this day. When it was built, it was the world's longest bridge for a while.
The height difference in the points of movement is the fascinating part, that there are the cliffs on the top and how there can be this movement on this upper level and the lower level. You know, it's a little bit nervous looking, especially if you've experienced it.
The bridge obviously fits in quite splendidly with the local topography. But it's a thing of beauty from an engineering perspective too, not just a scenic one. Its finished structure comprised of sets of triangles and gives the Dom Luis I Bridge its distinctive appearance. In the 19th century, the supporting structures of these massively ambitious engineering projects were worn proudly and on the outside. It was engineering architecture and its bold structures that inspired Le Corbusier in the early 1920s to write his manifesto Toward an Architecture, containing the famous advice, "Let us listen to the counsels of American engineers, but let us beware of American architects."
I think that's an interesting thing.
This one piece will make 52 layers.
Watch on mobile devices or the big screen. All for free. No subscription required.
This bridge in particular is very strong in its expression of the two types of visual movement of the arch and the straight parts. But it's fascinating that somebody would use this combination.
At any rate, the Dom Luis I Bridge was opened on October the 31st, 1886. And a year later, the lower deck, intended for normal ground transportation, was opened as well. Porto, in those days, was still at the crossroads of once popular trade routes. When the bridge opened, it was a welcome shortcut for weary travellers who had been used to traversing the deep valley of the River Douro. The city itself is no longer the market hub it used to be, but the presence of bridges in the Portuguese city is still a quintessential part of the skyline. The most imposing bridge of all is undoubtedly the Dom Luis I Bridge. Tower Bridge, London, United Kingdom. In the heart of historic London is one of the most famous bridges in the world, the Tower Bridge. It spans the River Thames, with Southwark on the south bank and Tower Hamlets, and the East End on the north side. The East End was originally located outside London city walls. It was a place where the ships had been built and repaired since the Tudor era. But in the second half of the 19th century, it transformed into a centre of industry and commerce. Building developers, industrialists, and immigrants all would benefit from a new bridge. A special expert committee was established in 1877. Eventually, the board announced a tender to which more than 50 proposals were submitted. The winner was the project from city architect Sir Horace Jones. He would die shortly before its completion.
The neo-Gothic style of this bridge and the combination of a suspended bascule bridge makes this piece of simple engineering work unique in this city.
The bridge's engineering works, with attention to the retractable deck, were drawn up by Horace Jones' chief engineer, a certain John Barry. Barry designed a two-tower bridge, where the two halves of the deck can be lifted up to allow a ship to pass through. To shorten the section of the deck which has to lift up, The bridge's two towers were set on pillars in the middle of the river bed, instead of on the river banks, as you might expect.
The confidence in it, the way it was designed, the confidence within which different systems of engineering were combined, it's even expressing how at that moment in history engineers could do it this way.
To protect the steel core of the bridge, some parts of the bridge were covered by Cornish granite and Portland limestone. The up and down bridge deck was initially powered by a steam engine, later replaced by engines installed in the tower's foundations. In order that passing ships not disrupt pedestrians, two separate covered walkways connected the two towers. After Horace Jones' death, the legendary George Stephenson, so-called father of the railways, took over the project. For one thing, he changed the architectural design of the bridge towers, which Jones planned to cover with bricks. Stephenson chose a more decorative style of the then fashionable Victorian neo-Gothic. London Tower Bridge, an incredibly elegant drawbridge, was open for business on June the 30th, 1894. The ceremony was attended by royalty, in this case the Prince of Wales, the future King Edward VII, and his wife, Princess Alexandra of Denmark. Anyone with an interest in the history of this beautiful engineering structure can visit the excellent interactive exhibition located inside the bridge. The Tower Bridge's high-rise footbridge with a modern transparent floor offers some of the most breathtaking view of the modern metropolis, London. Harbour Bridge, Sydney, Australia. Sydney, Australia's largest city, is renowned for its far from ordinary opera house, looking out onto Sydney Harbour, which of course is spanned by that architectural icon and Australian symbol, the Sydney Harbour Bridge. The idea for the bridge was first floated in the year 1914, the year the First World War broke out half a world away. That was when a certain John Bradfield, the chief engineer of Metropolitan Railway construction, came up with the idea of a cantilever bridge without piers, anchored on the seabed. But it would not be until 1930 that the bridge would finally be completed. The regulations from construction permits had to be rewritten to allow the bridge to be built. The tender to undertake construction was eventually won by the English company Dorman Long and Company Limited from Middlesbrough, which had rich experience in constructing large steel arch bridges. By 1926, the groundwork was completed to enable building of the massive foundations of the bridge towers. At the same time, deep in the ground next to the bridge piers, foundations were built into which steel cables were anchored to secure the bridge's unfinished arch from collapsing.
This arch bridge has a pillar at either end. These pillars also have another function, apart from supporting the load from the arch of the bridge.
Construction of the arch, known colloquially as the coat hanger, began in 1928. Over a period of 13 months, material and workers were transported to their destination by two large cranes moving on rails, and the arch bridge was painstakingly assembled. Thanks to flawless calculations and synchronized workflow, the two arms linked together exactly on August the 19th, 1930. After the last bits had been riveted together and the securing cables removed, cranes started to gradually enlarge the deck in both directions, from the middle of the arch. Finishing the deck lasted until June of the following year. The final steps included removal of all support structures, completion of the monumental granite pylons, and preparation for a load test. The load test lasted 3 weeks, during which time the bridge bore the weight of 96 steam locomotives.
The concept to show the technology of the time and to show the vaulting, the arch which is still suspending the platform below, was important. And there could have been other types of bridges there, but there was a desire to celebrate the passage there.
These days, the Kotanger is an extremely important arterial road. Every day, some 180,000 vehicles cross over it. In addition to its 8-lane road, the Sydney Harbour Bridge has 2 railway tracks, a bicycle path and sidewalk for pedestrians. If you appreciate unforgettable views, you can climb to the top of the arch of the bridge and look out over the bay and the city. This activity takes around 3.5 hours, but for many, the feeling of having the whole of Sydney at their fingertips is well worth it. Golden Gate Bridge, San Francisco, USA. San Francisco's famous Golden Gate Bridge has spanned the Golden Gate Strait for almost 80 years. It's a symbol of the city and of Californian cool. Yet the Golden Gate is subject to harsh weather conditions at times, with sudden gusts of wind, temperature fluctuations, and strong sea currents bashing against the shores. But the extreme environmental conditions were not sufficient to discourage Joseph Behrman Strauss, the spiritual and actual creator of the Golden Gate Bridge. Strauss, an American-born structural engineer, had the dream of building a bridge that would exceed all existing bridges in every important respect. His opportunity came when the city of San Francisco announced its intention to build such a bridge across the Golden Gate Strait.
The best results are achieved when an excellent architect and designer meets an excellent structural engineer, and everyone involved works together to develop the structure.
Work on the Golden Gate under Strauss's supervision began in 1930, with the cooperation of the engineer Leon Moiseff and the architect Charles Ellis, who lent the bridge its memorable Art Deco appearance. The most difficult part was the building of the foundation for the southern pillar. This is located 300 meters, 984 feet, away from the shoreline, some 30 meters, or 98.4 feet, deep. The next step was to build the massive foundation plate of the south pylon. No easy feat.
Problem of that bridge is that the weather, the clouds pull into the bay, they completely mask the bridge, and you have no feeling of its presence. But to watch the clouds disappear and the sun take over and illuminate this fantastic structure, you know, it's a very breathtaking experience.
After the completion of the concrete plates that are the bridge's foundation, came the construction of the towers, riveted from huge steel segments. For each tower, about 600,000 rivets were used. Workers on the bridge, charged with making sure every single one of those rivets was screwed tight, operated along an intricate maze of corridors with 90 different routes linked together by 27 ladders. Both pylons were completed in the summer of 1935. At 227 meters, or 745 feet, they immediately became the highest bridge structures in the world. In the autumn of the same year, springing of support cables began. The construction of the monumental bridge was at last completed. On May the 27th of 1937, the day the bridge was inaugurated, 200,000 citizens of San Francisco took the opportunity to cross the Golden Gate Bridge. Annual maintenance is the work of 28 painters, whose task it is to prevent corrosion at critical points. There's a myth that the bridge is being continuously top-coated, but in actual fact, it has been painted anew only twice. Nevertheless, few would dispute the claim that Golden Gate is among the most photogenic bridges in the world. The second half of the 19th century was a golden age of invention, with unprecedented advances in science and technology. It was largely thought advances in construction mechanics and metallurgy that projects only dreamt about before could be turned into very tangible reality. The following 5 bridges belong to the recent past. They can all be said to be associated with developments such as globalization that are particular to the last 50 years. Erasmus Bridge, Rotterdam, the Netherlands. The Netherlands may be a small country, but it undoubtedly ranks among the world powers, at least in terms of architecture. This country has a rich tradition shaped by generations of fine Dutch architects. But even today, the Netherlands has its architectural world stars. These certainly include the couple Ben van Berkel and Caroline Boos from UN Studio. It is their signature on the project that has become a symbol of the city of Rotterdam. The Erasmus Bridge is a fully functioning work of art in the centre of Rotterdam, bridging north and south. This elegant bridge sits adjacent to the routes of 2 motorway tunnels, Maastunnel and the Benelux Tunnel. Open since 1996, its asymmetrical pylon, shaped like an inverted letter Y, rises to a height of nearly 140 meters. The pylon shape, resembling the body of a swan, turns out to be functional as well as decorative.
For this construction, the CAD/CAM method was used. The construction concept and final plans were all created with the help of digital technology.
Because the pylon is not typically straight and conventional, instead being beveled at 2/3, the Erasmus Bridge is much less pressured by physical forces that impact it from support cables. The course of load moments by oblique stray cables is more even on the console pylon than on pylons of usual shapes. Even bending moments are significantly smaller. Originally, the pylon was to be made of concrete, but it turned out to be too expensive and difficult to make. So, in the end, the architects found a way to do it with steel. The southern part of the 6,800-ton heavy steel bridge integrates a 90-meter bascule bridge, which is considered the biggest and heaviest in Europe. The Erasmus Bridge demonstrates what can happen when architects and engineers follow a uniform design principle. These days, constructions like this take in urban planning, infrastructure and public relations. This was the 90s, when architectural software was just coming into its own. Architectural design begins with the initial sketches and ends in the final phases of construction. In this case, 5 differently shaped concrete pillars, fender, harbours, details, fittings, connections and service equipment all had to be designed. The interior of the bridge, which connects the southern part of the city of Rotterdam to the north, conceals a large concrete stairway leading to a parking garage.
Special architecture maybe even can be more remembered for its power at night, because you don't see all the limits that exist in the visual frame of reference during the day.
At night, this unusually subtle bridge wears its air of understated cool well, thanks in part to the play of lights. The Akashi Kaikyo Bridge, Kobe, Japan. The Akashi Kaikyo Bridge is the largest suspension bridge in the world. It is a miracle of Japanese construction and engineering, which links the city of Kobe to Iwaya on Awaji Island and is also part of the Honshu Shikoku Highway. The idea to connect Awaji with Kobe had emerged at the end of the 1950s in response to the tragedy which occurred in the Bay of Akashi in 1955. Collision of 2 ferries had claimed 168 victims. However, it took more than 3 decades before the bridge was built.
The task of engineering for earthquakes is an immense task, which is, for me, even till now, unbelievable how the techniques of engineering against earthquakes evolved and how they are sophisticated.
But it wasn't political or economic reasons which prevented construction for so long, but the right technological solution. That only came by the end of the 1980s, boom years for Japan. Akashi Bay is a place used to extreme natural conditions. The seabed around here is some 100 meters or 330 feet deep, and the shore faces massive tidal streams at up to 4.5 meters per second. It is close to major international shipping lines, but also located in a typhoon zone. Worse, the bay is located above the border of two tectonic plates and sees frequent earthquakes. These were the factors which had to be carefully considered when designing the giant bridge. The construction of the Pearl Bridge, as the link between Kobe and Awaji Island was nicknamed, commenced in 1988. Work began by building massive bases for the embedding of the load-bearing cables. Simultaneously, construction of the foundations of the future, 300-meter high bridge towers, began on sea. The towers are based 60 meters below the sea surface and composed of gigantic steel cylinders. It took 7 years to complete the two towers and to stretch the load-bearing cables over the bridge deck. When it seemed that the construction was progressing successfully to its completion, a devastating earthquake struck.
Because of the extreme conditions in the region, this bridge was designed to absorb shocks and tremors caused by typhoons and earthquakes. In 1995, an earthquake destroyed many buildings in Kobe, but the nearly completed bridge,
The unfinished Pearl Bridge, miraculously withstood the quake. The opening ceremony was attended by more than 1,000 prominent guests, including His Imperial Highness Crown Prince Naruhito and his wife, Princess Masako. Thanks to 1,737 lights installed on all parts of its structure, the Pearl Bridge lights up in practically any color. Olson Bridge, Denmark and Sweden. Olson Bridge is a critical component of a modern transport infrastructure that connects the Danish capital of Copenhagen with Malmö in Sweden. Altogether, it is over 16 kilometers long and consists of 4 parts: a 3.5 kilometer long underwater tunnel, an artificial, about 4 kilometer long island, a significantly smaller peninsula built up by the Danish shore, and finally the bridge itself, named after the Øresund Strait, which it crosses.
the gigantic proportions of this almost 8-kilometer long structure, the combination of road and rail traffic, and the fact that the bridge connects 2 states and 2 great cities, Copenhagen and Malmö, makes this construction one of the most interesting in the world.
The official contracts for building the Olson Bridge were signed in 1991, but the idea to connect the 2 countries is considerably older. Architects and engineers had been trying to solve the problem since the 1870s. The most logical idea seemed to be placing the bridge at the narrowest point of the Øresund Strait, between the Danish Helsingør and the Swedish Helsingborg, about 40 kilometers north of Copenhagen. There the waters are only 4 kilometers wide. Eventually, however, the current site was chosen, even though it was 4 times as long. Economic factors and transportation routes had a lot to do with the bridge's final location. Works began in August 1995, with its last part being fitted 4 years later. From a structural point of view, the Øresund connector frame is a mixture of suspension bridge and classical bridge. The length of the whole structure, which is the 2nd longest bridge in the world, is the remarkable 7,845 meters. The first day of July 2000 became an historic day for both Denmark and Sweden, as the Öresund Road and Rail Bridge was officially opened. The first train set off from Malmö to Copenhagen on July the 2nd, 2000, at 6:09 a.m. Vehicles had begun crossing the bridge the night before.
This kind of connection is about freedom. It's about freedom of movement. And I think the bridge, in that part of the world, the bridge has a completely different meaning. I think life probably wouldn't exist normally for them without these bridge connections. And this particular bridge is fascinating, that you come in or out through what looks like an artificial island in the water to cross this bridge. So I think it's absolutely amazing.
A combination of reinforced concrete decks with supporting trusses underneath was used in this construction.
Connection of the Öresund shores has not just fulfilled the old dream of the Danes and their Swedish neighbours of shortening the journey between Malmö and Copenhagen to just 35 minutes. It has created a completely new economic region. Gateshead Millennium Bridge, Newcastle upon Tyne, United Kingdom. The Gateshead Millennium Bridge is a pedestrian and cyclist tilt bridge that, once seen, is not quickly forgotten. It spans the River Tyne in England between Gateshead's Quays Arts Quarter on the south bank and the quayside of Newcastle upon Tyne on the north bank. Because of how it seems to open and shut to let ships pass through, locals call it the Blinking Eye Bridge.
It's the first bridge which turns around its own axis to allow ships to go through, and which, when necessary, can raise the whole pedestrian and cycle deck.
In point of fact, its appearance owes as much to function as to form. The whole bridge rotates on the huge joints embedded in the concrete struts on both banks of the river. By turning thus, the bridge allows for the passing of ships below. It's an unconventional solution, but one which really makes this thoroughfare for pedestrian traffic and cyclists one of a kind. The bridge is comprised of two main components: the bridge's structure itself and the mechanism that elevates, or more precisely, rotates it by a few degrees. The bridge is essentially made up of a pair of steel parabolic arcs, one of which is a supporting arch that carries the deck curved in the direction of the river flow using the supporting rods. On the deck, there are two separate paths ensuring safe passage for both pedestrians and cyclists. The elegantly shaped railing is reminiscent of luxury ocean liners from the golden days of cruise ship travel.
If this engineering can inspire people to move, to observe, to appreciate engineering, then it's successful.
The second part of the structure is, of course, the tilting mechanism. It consists of two large cylindrical pins. These not only rotate the bridge, but hold it together. The tilting itself is performed by 6 hydraulic arms. The tilting mechanism of the bridge consists of a pair of parabolic steel arches, one of which forms a curved bridge deck, which is held by the second one, utilizing a system of suspension rods embedded into the giant joints. Tilting of the bridge during which both arches act as counterweights, lasts less than 5 minutes. During this time, anyone waiting impatiently on the banks or at the helm of a boat should thank the sophisticated hydraulic system, run by 8 powerful yet energy-saving electric motors. Each time the bridge tilts, it tidies itself up. Earth's gravity causes all the litter to slide into special bins placed on the bridge deck. A competition to design the bridge was eventually won by the Wilkinson Eyre Architects Studio in London and civil engineering firm of Gifford and Partners. On November 20, 2000, the pre-assembled bridge was delivered to its new home location. Thousands of curious spectators watched its installation. It was performed using a giant floating crane, Hercules II, which was brought by towboats from the Netherlands. They were able to walk the bridge the very same day. The official opening of the bridge, which has since appeared on the £1 coin, was not held until May the 7th, 2002, with none other than Elizabeth II present. Evidently, bridges are a real drawcard for European monarchy. In 2000, the 850-ton bridge was awarded the most prestigious prize of the Royal Institute of British Architects. Mio Viaduct, Mio, France. The Mio Viaduct is a masterpiece of contemporary architectural engineering and a standout even among the quite stupendous bridges of the last few decades.
It definitely, for me, reflects French thinking, that if we can do something grand, if there's a reason to do something grand, and it's fits to the place, let's do something grand. Even grand doesn't mean overdone, but grand can be that let's do the best bridge that could possibly be built here. This is the thinnest bridge, the most narrow columns and towers, and this bridge expresses that.
When French engineers began a new stretch of the motorway A75 between the cities of Ferrand and Béziers near the town of Millau, they encountered what you might call a surmountable problem. There were several ways of traversing the deep valley of the Tarn River taken into consideration. A conventional concrete frame bridge was seriously considered, as were several types of truss and arch bridges. Finally, the designs of the renowned Michel Virologa for a suspension bridge with 8 spans were selected.
The collaboration between architects and engineers to apply new types of technology was very important during the whole construction of the bridge.
The designs of Virologa, one of the best bridge engineers of our time, drew on a combination of concrete and steel, which, if properly maintained, can ensure a working life of at least 120 years. Virologa opted to use steel and concrete, not just because of durability, but because he believed the bridge's finished structure would then be graceful and aesthetically pleasing. He invited the celebrated British architect Sir Norman Foster to cooperate on the final design. Thanks to Foster's artistic aplomb and Virologa's engineering skills, the bridge, despite its size, does not appear bulky. In fact, the contrary. It almost hovers over the valley of the Tarn River. The lightness and at the same time stability of the bridge is ensured by the huge concrete pillars resembling blades of grass. There are 7 of them, with the shortest being 78 meters or 253 feet tall. When you factor in the steel masts on which the supporting steel cables are fixed, the highest pylon reaches a daunting height of 343 meters. Each of the load-bearing reinforced concrete towers sits on 4 cylindrical bases. The lower part of the load-bearing tower is a hollow concrete parallelogram. At a height of about 90 meters below the bridge deck, the pillars divide into 2 hollow shafts in a Y shape for good reason. This solution increases the strength of the deck in its longitudinal direction, while reducing the stress caused by temperature change. After they were erected in 4-meter sections, the outer scaffolding slid off automatically and the inner scaffolding was moved with a crane. Supporting truss steel structures were constructed in between the pylons. At the top of each pylon, a specially designed sophisticated hydraulic lifter was installed, whose task was to lift the deck up at regular intervals and move it a few inches closer to the center of the bridge as it took shape. The construction of the bridge deck is an unbroken steel girder, supported by abutments and 7 intermediate pylons. Work on the deck progressed from both sides at a speed of about 10 meters or 33 feet per hour. After completion of this process, when both parts of the bridge deck had been precisely matched, welders connected the bridge and the steel masts bearing the supporting cables were placed on each pylon. The resulting Mio Viaduct merges harmoniously with its surrounding landscape, another example of how form and function mix. Today's great bridge-building engineering works would not have been possible without sophisticated computers, cutting-edge building technology, and new materials with incredible features. They are fascinating, breathtaking structures that often seem to deny the laws of nature. As long as we need to get from one place to another, bridges will remain inherently linked with the march of progress and of civilization.